Okay, in this final video, we're going to think about a third way to calculate enthalpy for a reaction, and that is called Hess's law. So just to refresh your memory, we talked about calculating enthalpy for a reaction by using stoichiometry. If we were given the delta H for a reaction, and then we could use molar relationships to figure out and stoichiometry, what it was for our specific situation. Then in the last video, we thought about calorimetry, which is really just heat measurements of heat transfer. And now we're going to think about something called Hess's law. So what is Hess's law, and how can it help us calculate enthalpy, or the heat of a reaction? This is Hess's law, and I don't have it typed on your note sheet, so you're going to want to write it down. But it basically says that if a reaction is carried out in a series of steps, not all at once, the enthalpy change for the overall reaction is equal to the sum of the enthalpy changes for the individual steps. Because remember, enthalpy is a state function, so it doesn't matter if we do it in one big step or in many tiny steps, either way, it's going to be the same. And if we do it in a big step, the change will be equal to if we had added up all the tiny steps. So let's see what that really means. So you have this picture in your notes, and let's talk for a second what this means. This is a diagram showing us the energy changes that happen when 1 mole of methane is combusted. Oopsies. Here I have methane, it's a gas. And it's being combusted, so it's being combined with oxygen, 2 moles of oxygen. So these are my reactants. I'm going to go ahead and write this over here. I have CH4, which is methane, plus 2 O2s. This is representing the reactants, methane combining with oxygen and combusting, and it's 2 moles of oxygen. When these combust, what do we make? Well, any time you have an organic, and that's what this is, carbon and hydrogen are organic molecules. Anytime an organic molecule combusts, you make only 2 things, carbon dioxide and water. Those are your products, and it's actually going to be 2 waters. And over here in the diagram, our products are written here. So in this particular, looking at this particular picture, the way they've drawn it, they have their reactants up here and their products down here. And if we look, going from reactants to products, we lose 890 kilojoules of energy. So this is exothermic, and its change in energy is equal to negative 890 kilojoules, the combustion of methane. Now, what if we did this in 2 steps? So I'm going to move my picture. I have this in words over here. Again, this is the reaction that I had over there in red. This is it. This is the combustion of methane. Methane plus 2 oxygens. When they burn, make carbon dioxide and 2 waters, and your net change is negative 890. Actually, let's bring the picture back. If we did this in 2 steps, we could do the first step where we went from methane and oxygen to carbon dioxide as a gas and water as a gas. See how here our final product, I should have written that in here, water is a liquid. So the state of a substance matters. In this end, the water is a liquid. But what if we had an intermediate step where we had our reactants make carbon dioxide and water as a gas? That's what this equation is right here. I'm going to circle it in blue. And the energy change for going from methane and oxygen combusting to carbon dioxide and water as a gas is only negative 802 kilojoules. Then, what if that water as a gas lost enough energy to become a liquid? Okay, it cooled down enough to become a liquid. Then that water, in this reaction, water going from a gas to a liquid, the enthalpy change would be negative 88 kilojoules. These 2 enthalpies, if you add them both up, they add up to negative 890, which is what we had for our total reaction. if we add up these reactions, and I don't think you've ever done this before, but let's add this reaction that's outlined in blue with the second one that I'm going to outline in red. So we're going to add our reactants. So I'm going to bring my methane down, I'm going to bring my 2 O2s down, and I'm going to bring my 2 H2Os down. Then I'm going to add all my products and put them all on the product side. So I have carbon dioxide comes down, 2 H2O gas comes down from here, and this 2 H2O liquid comes from here. Right now we're going to look at what we have and see if we have something on the left side and the right side, it's going to cancel out because we don't write things that are on the left side and the right side. So we do. We have 2 H2Os as a gas right here, and we have them here. So that's, if we have it on the right side and the left side, that's not part of our net reaction. So we're going to cross that out. So our net reaction, we can say, involves just only the things that are changing, the methane plus the oxygen making carbon dioxide and water. And the enthalpy change for this net reaction is negative 890. This picture shows it either as going in one step, or you can see this intermediate step, these intermediate products. So there will be one more video after this, but I'm going to stop this one now and then do the final part on Hess's law, the two sample problems in a separate video, so I can post this.